Okay, Corbinian Schlosser from Toulouse.
Hello, yeah, thank you for still being here. And yeah, one could say that there might be a comic picture of Popeye missing. No permission granted though, but it's still in the title. And I'll talk about polynomial optimization perspectives towards dynamical systems and why Popeye. Yeah, the last 2.5 years, I had sometimes perspective. When I was looking at some problems, particularly from dynamical systems, I was trying to put on the polynomial optimization lenses, and I hope I can show in some cases. Yeah, good. Okay, that's about the things that I enjoyed there. Okay. So first, I'll start with what a dynamical system is. So in this talk, I'll consider continuous time systems. That means, and they're finite dimensional. So they are given by an ordinary differential equation, x dot is f of x. And the function f maps from Rn to Rn, and this is known to us. And to a differential equation, we also need an initial condition. And there will also be a constraint set x, but you can really think of a box, for example, or choose your favorite set in Rn. And now for the question, how we can illustrate this. For example, let's choose the following system here. And one way of illustrating a solution to differential equations is the following. So we take the right-hand side here and do this following plot. What does this plot do? We take a point xy. And to this point, we attach an arrow that points in the direction of the right-hand side of the differential equation. Okay, and solutions to the differential equation now are curves that are always tangential to those arrows. So here's one. Okay, we verify. Always looks like the curve is tangential to these arrows, and this is exactly those are the solutions to this equation. Here is another one, and another one, okay, to get some idea of how we can picture those dynamical systems. Okay, what the outline or the goal of my talk is, I want to consider a dynamical system, but I want to embed this into a convex setting. So as I said, the function f here will be polynomial. So that means it can be nonlinear. And the idea is to embed this still into a convex setting, and later we'll see that this will even be linear. But I want to point out that this is not just linearizing the vector field by taking its derivative. This is a very classical approach, but I'm not following this. And there's also a good reason to it, because taking the derivative, replacing f with the derivative, of course, introduces an error, even though this error might be locally small. But this is not what we want to do. Another way that I'd like to advertise a little bit is looking at the Copeland operator. This is also not something I want to do, but since I want to advertise it, it stays here for one more slide. But what I want to present is doing an embedding by means of measures, and then using polynomial optimization techniques. So again, here, the arrows indicate that there are different tools to use here, for example, particle methods or Galerkin methods. But I took the choice to use polynomial optimization techniques because there's some advantages and some things that I find beautiful that came with it. And these can then be applied to several problems for dynamic systems. Some of them are stated here. One is, for example, if we're interested in invariant sets. So this is represented here. If we look at the blue curve, it has this property. If we take all the points on this curve, and if we flow those points for a certain fixed amount of time into the future, then we still get, as an image, the same curve. Another question relates to reachable sets. What is shown here on the right-hand side is I take initial conditions, x0s, all in the square here, and I flow them forward in time, and I look how does the system evolve, how does the set look like, where they end up. And here in that case, I ended at maybe at 20 seconds down here. Okay. And for cases where I'm interested in reachable sets for certain times, say, for example, now we start in the red box here. And to illustrate what I'm looking here at is, so the next deformed rectangle now shows the image of the first red rectangle after half a second. And I can evolve further in time for another half a second and so on and so on. And in case I'm interested in those evolutions of certain initial conditions, then I'm talking about reachable sets. Another question is optimal control. So here I give a very simple example. In that case, the question is, we want to start in our red box and reach the yellow star as fast as possible. And the question is, where should I start that in order to arrive at the yellow point as fast as possible? And here we see, if I evolve the red box for 1.5 time seconds, then I get this orange deformed rectangle, and I see it really touches the yellow star. So this shows me that this gives me a solution. And after 1.5 seconds, I arrive at the star, and this picture also tells me where I have to start, namely in this lower corner. And I think I also would like to take the chance to promote this even more. This is a very nice geometrical property of such problems, namely that I have to start on the boundary here in order to reach this point the fastest. But for the rest of the talk, I want to focus on so-called attractors. And these I want to illustrate in the following. So the main idea is attractors, they characterize where points eventually flow to. And I have a video here. Yeah. So here I took just a random set of initial conditions, and we'll see how they will evolve in time. So they just follow the differential equation. And slowly we see they approach a shape that we've already seen before. Yeah, and again, here there are also nice things to say about the attractor itself, of the form, and in that case, it's even one single trajectory. It's a periodic orbit. But you can also see here, for example, the particles move faster, so the density here in those areas is less than in the areas where it's moving slower. So there are also many interesting questions about attractors itself. And yeah, and I want to motivate the following approach at the example of such attractors. Okay. So this is the main goal. We want to compute the attractors, mostly their volume, but also their shape. And in order to do so, I should define attractors. And then I present an infinite dimensional but linear programming problem that can do so. And as a second part, then, in order to motivate another technique where polynomial optimization was used in the past already, we observed some qualitative disadvantage of the particular LP that I stated first. I show that this can be improved. And finally, I'll address complexity issues and how they can be overcome in some cases when there is enough sparsity or symmetry, for instance. Okay. So what is a global attractor? It's a bit technical. There are several notions. Each different notion gives a different attractor object. I'll focus on this one. So a global attractor for a dynamical system. Dynamical system, this is constraints at X, they are a box, and the vector for that. So we denote the global attractor by the smallest compact set that attracts all trajectories in a uniform way. Okay, so here, one has to be careful. If we look back at the video here, and if I fast forward a little bit, we see that there are some particles that take really a long time to reach the outer curve here. And this is because they start in the middle where there's not much dynamics happening. There's low velocity. So in fact, for the system I'm showing here, the attractor is not just the outside curve that we are showing here. In fact, it's rather the whole set. So by this, I just want to highlight that the notion of attractor is subtle and really depends on what we're looking at. If we choose a different notion of attractor where we only want that each single initial condition converges to the set, then we indeed would get the left picture as an attractor, but this depends on the notion. Okay, And with Milan, we proposed the following infinite dimensional linear programming problem. It's of this form, and it acts on measures. And it has infinitely many constraints. So we test for all continuously differentiable functions phi. So that basically means this here is a weak representation of an operator equation. And I don't want to go too much into detail what this LP exactly does. I'd say there are two ways to motivate this. One is to characterize the attractor as the intersection of two sets that are already understood in the sense of such linear program problems. This was done by Milan. And then you just have to patch those two LPs together and you arrive at this. But then if you want to understand where those LPs come from, the main idea here is, in fact, we already know what the solution should be. So what we want to have is mu0 should be the Lebesgue measure, which is lambda here, restricted to the attractor. And mu hat should be the Lebesgue measure restricted to its complement. And mu plus, and the decision variables mu plus and mu minus, they're just the so-called occupation measures that correspond to this. And the idea here is that we already know what the solution should be like, and the constraints are hopefully strong enough so that they really single out the solution that we want to have. And that this is true, this is a nice superposition principle by Ambrosio. So there's some nice analysis tool somewhere hidden. And for this LP, we showed that it really gives us the volume of the attractor. The theorem here, but there is also a downside. As we've seen before, attractors sometimes they can really be just curves. So it's very typical that their volume is just 0, and as a consequence, in many cases, the trivial solution where I just set the measures to be 0 is already optimal. So that means I don't gain so much information about the attractor itself, except from its volume, from optimal points. And this is something I would like to improve. And fortunately, because I want to show you such nice pictures, in my opinion, and this can be improved by looking at the dual problem. If we formulate the dual problem to this one here, it acts on continuous functions or C1 functions here, and it has the following form. And we have still the property that it computes the correct volume because there is no duality gap. But additionally, it has a nice qualitative feature, namely, whenever we take a feasible point, so if we take a triple here that is feasible for this problem, then if we look at the super level set of the first component of this triple here, then this encloses the global attractor. And even better, if this triple gets optimal, and if the corresponding cost converges to the optimal value, then this enclosure gets closer and closer to the attractor and converges to it with respect to the Lebesgue measure discrepancy. And this is exactly the way how we were able to compute such pictures. So what you see in the picture in black is the attractor, the so-called Lorentz system, and the area in red around it is what we obtained by looking at such a super level set. Okay, and to put this to put the process on a frame, what we do where we formulate a primal linear programming problem on measures, and this we can do because it's well motivated by the techniques from occupation measures. But there we see it does not have enough information about our attractor. Hence, we also look at the dual. I mean, we should always do this, but in that case, it turns out that the dual problem gives us very good properties for the attractor. And now, once we have guaranteed this, we look at how to compute and how to solve these problems. That means on the primal side, we look at moments, and on the dual side, which acts on functions, on continuous functions, we restrict to polynomials. So here on the right-hand side, there's something to do, but the main idea is that when restricting to polynomials from continuous function, all the continuous functions restricted to polynomials, we use the Stone-Weierstrass theorem, and that the solution set is full dimensional. And this then gives generalized moment problem on the measure side, and a sum of squares problem on the polynomial side. And for this, yeah, we've seen this much before. How we solve this, we truncate, get sequences of STPs. And in all this process, the enclosure property that we have for the function side LP is maintained. So even if we solve for SS polynomials, we still get enclosures of the attractor by the super level sets, as we've seen here. So this holds true in the same way if we restrict to polynomials. Okay. But on the other hand, there's a qualitative disadvantage of the problem that I had. So this again was the problem that we had before. And again, not so important how exactly it looks like, but the idea was we solve it, we restrict to polynomials, truncate the degree, solve it using S to S constraints because there are inequalities. And for the optimal polynomials that we obtain, we look at those super level sets, and these we choose as approximations of the attractor. And we see that this works asymptotically, but there's a feature that is not always satisfied, namely these sets, they don't have to be positively invariant. And what does this mean? A set is called positively invariant if whenever I take an initial value in this set and I flow it forward in time, the solution stays in the set. I mean, this gives a qualitative property, and for many applications, this is useful. I mean, if you think of cars, for example, then it's nice if you know that you will for sure stay on the road and not take a detour somewhere else. And why I took this way of motivating the next LP that I will state is because it also shows a different approach to dynamical systems via polynomial optimization namely there is a certificate for invariance of sets using functions, and there's a classical approach then to, instead of using a general function that I'll explain in a second, using sum of squares polynomials instead. Okay, what is a certificate? This is via so-called Lyapunov functions. A function B is a Lyapunov function if it's defined on an open set. It's real valued, but takes only values in the non-negative axis. And it satisfies this gradient condition here, which basically says that solutions of the differential equation, function B decays along solutions of the differential equation. So if you want, you can interpret the function B as energy in some sense. And finally, we call it a Lyapunov function for a certain set K, if K is exactly the zero level set of this function B. Okay. And whenever we find a Lyapunov function or a Lyapunov function for such a set K, I mean, a function that satisfies these conditions and that vanishes on the set K, then we know that this set K has to be positively invariant. Okay, and this motivates the following approach. Namely, what we want to have, I want a set like this that is additionally invariant. So what I would like to do is I like to search for a Lyapunov function that vanishes on this set, or maybe even a smaller set. And how do I search for such a Lyapunov function? I replace everything here by sums of squares. Since I have inequality constraints, I hope to represent this by sum of squares. Okay. And the final part is there's an additional very intimate connection between Lyapunov functions and attractors. Namely, I can even characterize attractors by means of Lyapunov functions. This is done by this well-known theorem here. It says the attractor is the smallest set for which I can find a Lyapunov function. So that means whenever I have a function that satisfies the previous constraints, here this gradient thing here, then its zero level set is containing the attractor, but I can also find a Lyapunov function whose zero level set is exactly the attractor. That means that motivates the following optimization problem. So in order to compute the volume of the attractor, I try to compute the volume of zero level sets of functions that satisfy this gradient decay condition. But there's a fundamental problem with this approach if I want to do polynomial optimization. Namely, what I would like to do is I replace the set of C1 function by a set of polynomials and then apply, and then I would like to solve this by sum of squares techniques. But it can happen even for the easy case where the attractor is just a single point that I cannot find a polynomial Lyapunov function. This was showed by Amadi in very nice techniques, I would say, two-dimensional even. It's very geometric. So, but this already seems like it's ruling out this polynomial technique to use this technique in general. So, I mean, there are still examples and even conditions when I can find a polynomial Lyapunov function, but in a very general case, this might not be the case. But fortunately, there are ways around this. We relax our problem a bit. We introduce a perturbation parameter epsilon. So what I want to do is now, instead of solving the previous equation where there was no epsilon, now I allow here some epsilon term. And the consequence of this is that I allow myself some error. And now using the Stone-Weierstrass theorem, I can put some polynomials in there which solve this problem. And therefore, this problem still gives me the volume of the attractor. And I can find feasible polynomials for this set. And this was proposed by Jones and Pete. But what still was the case is that I need to evaluate this cost function here. I've taken the volume of a sublevel set, and this is difficult to do. This is non-convex, and therefore this problem is not easy to solve. But what we've done then is using a bit of techniques from the linear programming problem that I've presented before, namely, it's possible to linearize this by introducing some additional decision variables, and we arrive at this a bit longer problem. So there are some more constraints here, and I have to add a penalty on epsilon, but unfortunately this is an exact penalty method, so I really know for penalizing the epsilon by the volume of my box set, then this problem here really gives me the volume of the attractor. And still to remember where it comes from, the idea is that I want my epsilon to be 0, but I can't do this because then I don't have polynomial solutions. So that's why I introduced this epsilon error, but then I want to penalize this because I still want this epsilon to be small or 0 heuristically. And we showed that this problem indeed does the job. And yes?
You don't assume anything on the boundary of the attractor. That it doesn't have
I mean, it can even happen that the attractor is 0 dimension, has 0 volume. And I mean, this is also the case why we look at the dual, at the LP on functions, because the primal problem of measures that doesn't see much if the volume is 0. But here I don't need to assume much. I have to assume something in order to get what I wanted, namely in order to guarantee that the approximations that I get for the attractor. So this is this thing stated here. It's an intersection of 3 sets. But in order to make them really invariant, I mean, this is what I wanted. I have to check if this contour set here is contained in the interior of my box. And if this is the case, I get really what I want in the invariant sense. But I don't need conditions on the geometry of the attractor or its boundary. But of course, I think this enters, because if the attractor has a strange topology or strange geometry, then it will be much harder to capture this geometry by polynomial. So I would expect to have the need for to go higher in this hierarchy in order to capture the attractor world. You don't seem so convinced?
No, but I don't understand, because in the beginning you said that the solution of the LP was the Lebesgue volume. I mean, the optimal value was the Lebesgue
Yeah.
volume. But still,
Which is typically 0.
Yeah.
Yeah. Yeah. So the optimal value is not the interesting part. It's rather the approximation that we get by using these sets. Okay. And then in the final part of the talk, I'd like to address computational complexity. So yeah, we solved this. We have this LP, we truncate it, we fix the degree. That means we arrive at the hierarchy of semi-definite programs, and the largest block that appears has size n plus k half over k half, where k is the degree and n is the dimension of my state space, so where this box is living. And in order to get convergence, I mean, this result only holds asymptotically. We cannot expect finite convergence. The degree has to go to infinity, but yeah, we see and the scales very badly. So that means dimensionality reduction is needed, and there are different ways to this. One is using symmetry, for instance, and the other is sparsity. And the good case about symmetry is if the system, my dynamical system, carries some inherent symmetry. For example, the vector field carries some symmetry, and I have good symmetry of my set X. Then I can exploit the symmetry, reduce the dimension of my problem without sacrificing accuracy. And for sparsity, I'd say there are two different approaches. One is looking at sparsity features of the resulting problem from an algebraic perspective. We worked on this with Ji Wang, Victor, and Nina, where we apply term sparsity to this problem. And the other sparsity feature that can be exploited is sparsity on the dynamic system side. So can I somehow distinguish if my differential equation, in fact, decomposes into some smaller dimensional differential equations? And these two approaches, they don't coincide, and they can also be combined. And for the second one, I want to illustrate this basic and simple example. So suppose we look at this system here, and it carries some sparse structure because we're not using so many variables. And what we can see here is that the dynamics of the second state does not depend on the third state, and similarly for the third state. The dynamics of the third state does not depend on the second state. So they don't see what happens to the other one. So for example, if we leave on Friday, and then people are going back to Germany, Italy, or somewhere in France, then how this could be interpreted is what happens, or a traffic jam that happens in Toulouse once we arrive there. This is independent of traffic jam that happens in Amsterdam, because the Amsterdam team is getting there. So I can really separate those dynamics. And we try to show this by looking at certain graphs. What do they mean here? We draw arrows from one node to another whenever the node where the arrow is outgoing influences the dynamics of the node where the arrow is incoming. And by using this, we can look at general graphs or dynamics and try to understand which nodes don't really influence other nodes, where there's some causality that's happening here. And for such an example graph, it can be distinguished that here, all those groups that I find here, colored in blue, they don't influence each other. So there's no causal relation from what happens here to what happens here. So they have dynamics here does not directly or does not influence what happens here. So that means in order to, if I want to know what happens here, I can take I don't have to consider the whole system. I can chop off the other blue ones, and similarly for the other case. So this allows me to reduce the dimension in my problem. Yeah. And we applied this to some examples. So what you see here on the left is something that almost looks like an attractor that we've seen before. And yeah, 9 different versions of it. So we really try to, I mean, this is an artificial example where we enforced this very sparse structure, and we could solve this up to dimension 20, which would not have been tractable if we would have a full connected system. And then we even pushed this a bit further, but there's nothing much more happening. We just we did the same example, but we had more sparse outgoing leaves, and then we could solve something in dimension 52, which is went further from tractable in full dense cases. But I mean, this shouldn't make one too optimistic, because clearly there are systems that don't have sparsity, or where sparsity is harder to obtain. Matteo Tacchi, for example, worked on cases. The sparsity structure that I assumed here is very restrictive, and even systems that look sparse, they don't satisfy the sparsity that I need here. And Matteo was looking at one nice example, for example, where this sparsity approach that I stated was not working, so there are more and deeper ideas needed. But there are also systems like one on the right here. This can be social graphs, for example, that are very well and densely connected. So here, sparsity does just not appear. Or sometimes systems are still too large. For example, I've heard that for quantum computing, they like to consider 2 to the power of 52 dimensional systems. Even if there is a lot of sparsity, I would not recommend using sum of squares hierarchies. I don't even know how they would. I mean, I don't even know how you can treat such systems. I guess even storing information in that dimension is difficult. But with that, I want to conclude the talk. Here's some references, and I want to explicitly say thank you in some of the languages here. I can't remember it, how to pronounce it, but these were the words of thank you that I came in contact through my time in Poema here, and yeah, so I mean it when I try to say it in those languages.
Are there any questions?
So in the pictures you've shown, you had 2-dimensional pictures, but the dimension was 20 to 52. So
No,
maybe I didn't understand the pictures.
Okay. This one's.
Yeah.
Okay.
No, not the one. The attracting region, the one before. That one.
Here.
So
Okay.
dimension, space dimension is high, but the picture is a dimension 2. So
Yeah, but there are here on the left, there are 9 pictures of dimension 2, and what this means is I have 9 decoupled systems. They are all 2-dimensional, and they're in fact fetched together on one additional 2-dimensional thing. So that's why I end up in the dimension.
Other questions? Harish?
So you say you use a stone bias theory, but that's pretty vanilla. Have you tried something fancy like Christopher double kernel theorem, and sometimes used for polynomial approximations or approximating stuff polynomial?
When I use the stone bias theorem, I use it in order to guarantee that I can restrict to polynomials, to make sure that it's feasible to look at polynomials. I mean, this is not always the case once my feasible set does not contain polynomials, for instance. And the way I came across the Christopher double kernel was often for approximating the support of measures, which is something I would like to do if my LP would give me enough information. But here, for example, my measures are trivial. So the problem is the support of my measure, even though this is where the motivation comes from, but the support of the measure does not necessarily need to give me information about the attractor. But if this would be the case, I would like to use the Christopher double kernel on this problem, for instance. But unfortunately, the support of the measure does not need to enclose the attractor in this formulation.
Other question?
It's in question. So this is Lorentz attractor? or
Yes, yeah.
It's 3D.
Ah, yeah, okay. So this is a projection of the Lorentz attractor. Normally it's 3D, but this attractor also is not three-dimensional. It has I think it even has an irrational dimension, which also tells you that the volume is 0. But a beautiful thing to look at if someone.
But it's not a projection, it's just a 3D picture put on a slide. Right?
What's that?
This is actually a 3D picture that you just put on a slide. Right? So it's not a.
Yes,
it's
yeah,
not
okay.
a
So we
projection.
computed the three-dimensional approximation of this, but then we projected it onto the 2D slide.
But so how is how the level set works? So you say you get some functions.
Mhm. Yeah, yeah.
So level set gives some outer estimation.
This is the one that the area that you see in red.
Yeah.
The black is the attractor, and the red part is the set. Does this answer your question?
But in how does it approximate in 3D? Is the approximation good in 3D? We cannot see much.
Okay. Yeah, okay. We showed that it converges with respect to the volume. What we couldn't show is that it does not necessarily need to converge with respect to Hausdorff distance. So we couldn't guarantee this. But the examples that we used or where we looked at, it really looked close. If you look at the three-dimensional picture up here, and if you rotate it, then the red part really looks close to the attractor.
Okay.
I think Bernard wants to see some good 3D picture.
Yes.
Oh la la. Okay. Oh, just I have a good excuse. This is not my laptop, so I don't try. Okay, yeah, but this is a good point. I think it would have been nice to show the three-dimensional thing and being able to rotate it. And this is a very good point. Thank you.
And maybe related with you have a control of the speed of the dimension.
Yeah, thank you. Yeah, very good question. And with Matteo, we were talking about this using Gauss and Lorenz's convergence speed result. And the main idea or something that is needed is we have, in order to use your result, we would like to have some strict positivity here. And fortunately, this is possible because of the explicit form of the constraints. We can just add some epsilon to those W, and we can also add some epsilon to the function B's. And in the end, we make this strictly feasible with some epsilon. How did you call the epsilon error thing? This epsilon of f, yes. So we can explicitly create some positive epsilon of f while not damaging much the optimal cost. So by using this, we think that we can obtain some convergence speeds result, but currently, Matteo, we're looking into this.
Matteo?
So here you're computing out approximations of the attractor, and in simpler setting where you don't compute an attractor but simpler object, for example, the visual action. You can also do an inner approximation, as we have showed in the next paper.
Yeah.
And I guess that in that setting it will become very nasty, or because your attractor can have zero values. So what happens if you try to do a linear approximation?
I think one problem is that these attractors they easily end up being not semi-algebraic. So and very small in some sense. So having inner approximation could make it very difficult already from the perspective of that the sets they wouldn't like to allow you this. And I've seen your paper for the region of attraction. I couldn't see if it works with similar methods for this case, but I think there is this fundamental difficulty that these attractors can be small and bad.
No, just commenting your very last remark, you wrote 2^52 quantum
Yeah, okay.
dimension of quantum space, no? Because looking that quantum computing, it look discouraging. But if in principle one have quantum techniques, this should be doable, no?
Yeah,
50. Yeah, this is 2 to 252 times, but.
Yeah, I think this is somehow they also want to motivate us, but I don't know how well those STP methods can be applied on quantum computers. But if so, if someone knows, please come back to me. I would like to respond to people who told me like, oh, but in dimension 2 to the power 52, you're lost.
So
Yeah.
does this come from IBS?
Yeah. Thank you.
No, I don't know an algorithm, of course, but in principle, 52 qubit could be a reality.
Yeah.
No?
I think once this can be STPs can be solved fast on quantum computers, then how we could solve something in 52 dimension very sparse here, we could do the same thing in 2 to the power of 52. A very optimistic perspective.
Last question. If there is none, then let's end the speech.